Hi. So today I wanted to talk about the chi-squared test for a distribution. So what is the chi-squared test? Well, first of all, it's a test of the goodness of fit to a function. So in your book, what they're generally doing is testing to see how well different distribution functions fit different data sets. But it could be used for any function, and it could be used for any data set to any function. So for example, if you want to know if something is an exponential fit, then you do a goodness of fit for that, or a polynomial, or what have you. So any function, you have data set, you want to fit it, you want to see if that's a good fit for your function. I do want to caution you though, the chi-squared test is really not something that you use if you already know that the data should fit an exponential or a linear or whatever kind of function that you're in. If you know that it fits, then you don't do a chi-squared test. When you do a chi-squared test, what you're looking to see is if the data is fit by a certain kind of function. All right? So let's just say, for example, that we're seeing about some random function y is equal to f of x, and we have these xy data pairs, we have n of them, and we want to see if this data is well fit by this function. So we're going to assume that our xi values have negligible uncertainty and that the y values have a known uncertainty, and I'll call that sigma sub I. Okay? So we define our chi-squared in the equation at the bottom of the screen there as the sum over all your data pairs of your y value minus the fit at that point, f of xi, and divided by the uncertainty in y. And then you square that. And then you sum those squares for all your n xy pairs. So if you look at this definition, then you can see that you would expect each term in the sum to be roughly 1 or close to 1, okay? And that's because you would expect for a good fit and for small errors that your y value, your measured y value, would be pretty close to the fit value at that point, right? So if it's a good fit and your errors are nice, then you're going to have yi equaling f of xi plus or minus your uncertainty sigma I. So that means that if you calculate your value of chi-squared and it's much greater than n, which is the number of data points that you're summing over, then you've got a bad fit, okay? Because that would mean that your fit isn't good. Your residual, in other words, is pretty large for a lot of those data points. This definition works really well for a general fit to a function, because in an experiment you have measured your xy values, you know what they are, and you should know your uncertainties based upon your equipment and what's going on with how you acquire your data, your experimental uncertainty. You should know that. So it should be pretty easy to calculate your value of chi-squared. Okay, now in fitting programs and spreadsheets, however, they like to report what's called the reduced chi-squared. Now, why do you want to do that? Well, because if you have n xy pairs, then you're going to get a value of chi-squared that's close to n. Okay? So we want to normalize that number, all right, so that you can compare it to some standard. So it's better if you can compare it to a standard. So the way that we do that, to normalize it, to compare it to the standard, is by calculating the reduced chi-squared. And what we do is we take the value of chi-squared that we've calculated and we divide that by what we call the number of degrees of freedom, d. Okay? So this is the reduced chi-squared, and the number of degrees of freedom is equal to the number of xy pairs you've got, n, minus the number of constraints, c. So it's d is equal to n minus c. So n, number of xy pairs, c, the constraints, that comes from how many parameters you have to solve for when you fit the function. So for example, if you're fitting to a polynomial that is, say, second order, it goes up to x squared or whatever, then you've got your intercept, your slope on your linear term, the thing that's multiplying x, and then the coefficient that multiplies x squared. So you've got 3 constraints there, and we'll talk more about this as we go along. The number of constraints will depend upon what kind of function you're fitting, right? So for a polynomial that goes up to order p, right, that goes up to power p, then you're going to have p plus 1 constraints for that polynomial, and it'll change. If you're fitting to an exponential function, y is equal to a e to the bx, then you've got 2 constraints for the thing that multiplies your exponential, and then the coefficient in your exponential. Okay? For a good fit, your reduced chi-squared is going to be roughly 1-ish, right? Less than or equal to 1. Okay, so once you finish dividing out by the number of constraints, a good fit for a good value for reduced chi-squared is about 1, and that means that your function is well fit, or your data is well fit by the function that you've chosen. All right, so I wanted to do an example. Words, but examples mean a lot. Okay, so what I did was I made up a little projectile motion data set. And the way that I did that was I say I'm mapping my y values, my height values. So my y final is equal to y initial plus v initial t plus 1/2 at squared. That's our quadratic that describes the motion of an object. And I'm going to set my initial, I'm going to say that my initial position was 0, my initial speed in y was 40 meters per second, and of course the acceleration due to gravity is minus 9.8 meters per second squared. So then what I did was I generated a perfect data set, and then to generate experimental data, I just went off from my perfect values by a little bit, and I generated this fake data set for my y values, okay? So now I know exactly what function I'm trying to fit here, and I did this routine in Origin, okay? So this is all done in Origin, and I'm going to make this file available to you underneath the lecture so that you can see it. All right, so there's my data. Now what you do in Origin, let me pull this up. If you want to fit a data set, you click on it, and then you click Control for your measured values, and then you can go into Analysis, the Analysis tab, and then Fitting, and then you choose the fit that you want to do. And of course, here I'm fitting to a polynomial, so I choose polynomial, and then I open dialog. All right, so I've already done this. All right, I've already done this, and then a new sheet will open with the information about your fit. Okay, so let me go back to my lecture here. I've cut and pasted it in there and tried to make it a little bit bigger than it is on the Origin screen so you can see it. So here's what comes up when you fit it, and it'll automatically generate your chi-squared value in the statistics. Okay, that's automatically done for you in Origin, and most other fitting routines will do the same thing. It'll automatically bring up this value of chi-squared for you. Now here in Origin and a lot of other programs, they call it r-squared, sometimes they call it x-squared, just whatever symbolism they want to do. But anyway, here's your adjusted or reduced chi-squared. Okay. So the value of chi-squared here is 0.9986. That's pretty close to 1, and so we know in general that, of course, this function is very well fit by a polynomial, which is something that we knew anyway. We know that the motion of a projectile follows a parabolic trajectory here on Earth. We know this. Okay, so here's our value of chi-squared. It should be close to 1, and it is. All right, now how Origin and many other fitting routines calculate this value, okay, if you go back to what our definition of chi-squared is. Let me pull that up just one more time to remind you. Oops, sorry. Okay, so here's our definition of chi-squared. You're taking the actual measured value and subtracting off the value from the fit, and then dividing by an uncertainty, and then you're squaring that for each one of your xy pairs. All right, that's what you're doing. So I had here, you can see 17 xy pairs. Right? So the fitting routine, it automatically fitted it. It calculated what the intercept and the two other fit parameters are, the coefficients that are multiplying t and t squared. It calculated those coefficients. All right? Then from that value, you can see here it reported it. So the intercept and then the thing that's multiplying t and then our t squared, and those agree very closely as they should because I made up the data with what we have. So our intercept was pretty close to 0. The value of the initial velocity, which multiplies t, is pretty close to 40, and then we have minus 4.9 for the thing that's multiplying t squared, which is 1/2 times minus 9.8. So it's a decent fit. Now look here, the number of data points, that's the number of xy pairs, that was 17. That's our value of n. And then here you have the degrees of freedom, which is d. d is n minus c, okay? And that's 14. So you can see from the data, it had to calculate 3 different values, all right? The intercept, v1 and v2, as they're listed here. So the acceleration, the velocity, and then the initial y position. So that's 3 constraints. So c is equal to 3. So the number of degrees of freedom is 14. Okay? So when calculating your reduced chi-squared for this value, your number of degrees of freedom would be 14. Right? Now here you might say, well, what uncertainty? There was no uncertainty listed there. How did they get that, and what did they plug into the formula? Okay, well, that's a good question. So what they've done here, when you calculate a reduced, or when you calculate a chi-squared using a fitting routine, it does the fit, okay, and then it calculates from the residuals of the fit what your variance is in your data, okay? And then the square root of your variance is your standard deviation, and that's what it plugs in for your uncertainty. So if you don't specify an experimental uncertainty, then the fitting routine will supply one based upon how good the fit is, okay? And that depends upon the residuals between the fit and what your measured data point is, all right? Now, you can fix that. If you want to specify a specific uncertainty on each of your data points, you can certainly do that, okay? Let me show you how to do that. So what you do in Origin is you go in and then you make a column called uncertainty. Let's just say, for example, that the uncertainty on each one of those measurements was about 1.1 meters, okay? And I picked that because it matches very well what the variance was from my data, or the standard deviation of my residuals were from my data. So that gives me 1.1, okay? And then how you do that, you specify that in Origin. Let me pull this up for you, okay? Go back to my sheet. Look here, I've already done it, but you can click on it on your column and then right click, and then you go to set as, okay, and then you can pick X or Y error and specify it for that column. And then what you do when you do your fit is you just highlight all of the columns, okay, you highlight all of your columns, and then you go to analysis and you go to fitting, and you can do your polynomial fit here, open the dialog, and then what it'll do is it'll allow you to do errors as weight, and then you can choose that in your fit options to be from your spreadsheet, okay? And that's how you do that if you want to specify that. Okay, so there's an example of a chi-squared or reduced chi-squared for a fit to a general function. Now, your book is concerned a lot with how to fit chi-squareds to distribution functions. Okay, so we've studied the Gaussian, the Poisson, and the binomial distribution functions so far. Okay, so those are the three. If you're testing the fit to a distribution function, instead of the xy pairs for each data set, instead of the number of xy pairs being your value of n, now you're going to assign the number of bins in your histogram as n. Okay? So here, your value of chi-squared is going to be the sum over all the bins, 1 to n, of these values, OK minus E sub k squared divided by E sub k. Now, O sub k is the actual number of data points that you have in bin k. Okay? And then E sub k is the number of data points that you would expect to be in bin k if the distribution were a perfect Gaussian distribution function or what have you. Okay? So that's the expected number of data points in bin k. Okay, and then to calculate the reduced chi-squared, you're going to use the same formula. The reduced chi-squared is equal to chi-squared over d, except now n in the formula d is equal to n minus c. N is the number of bins, and c is still the number of constraints, but it's the constraints that come from the distribution function for itself. So for example, if you were doing a Gaussian distribution function, then you would have the mean and the standard deviation that you would have to calculate from your data, okay, in order to fit to that Gaussian. And so you have two constraints, your mean and your standard deviation, all right? And it would depend upon which distribution function that you pick as to how many constraints and what those constraints are. Just like the last time, though, a good value of a reduced chi-squared indicating a good fit would be roughly 1. All right, so I wanted to do an example problem for you with the distribution function aspect of chi-squared. So in the example that I'm getting ready to show you, what I'm doing is I'm testing to see how well the final exam scores from 2210 and 2005 fit a Gaussian distribution. So I'm going to calculate the average and the standard deviation for that data set, and there were 16 students, and then I divided those students into 4 different bins, okay? And then counted the number of score in each bin and calculated my chi-squared and my reduced chi-squared from that. So here's the chi-squared example. Let me maximize that here. Let's see if I can do new Let's go to something larger so hopefully you guys can see. Okay, so here we go. All right, so here's my scores in this column A. In my first column, all my scores are shown. Okay, so from that I can calculate my average and I can calculate my standard deviation, which are given here. So my average was about, my class score average was about an 85 with a standard deviation of about 10 points. Okay, so that's what I got. Then what I did was I said, okay, that's the center of my distribution function. And I divided it up into 4 bins. And so I divided it up by the number of standard deviations away from the mean that I was. So from 2 standard deviations away from the mean to 1 below the mean, then that was bin 1. Okay? And then from 1 standard deviation below the mean to the mean, that was bin 2. And then from the mean to 1 standard deviation above the mean, that was bin 3. And then from 1 standard deviation above the mean to 2 standard deviations above the mean, that was bin 4. All right? Now, if you remember your Gaussian distribution functions, then you know that between plus or minus 1 standard deviation away from the mean, that's about 68% of your data. Okay? So in bin 2 and bin 3, they go from 1 standard deviation below the mean to the mean, so about half of 68 or 34% of the data should fall within bin 2. And then from the mean to 1 standard deviation above the mean, that should be about 34% too. Okay? So I can calculate the expected number of data points for each of these means based upon Gaussian distributions. Okay? So 16% of the data should fall below that, right? And then 16% of the data should fall above that. All right, so that's what I've got there. And I've calculated the number of expected data points in each bin, okay, for those 4 bins. So those are my E sub k values, and I call them E1, E2, E3, and E4. Okay? All right, so from there, I then have the number of data points that actually fall into that. So I just went through my data and I calculated, or I just counted up how many data points would fall into each bin. So in bin 1 I had scores less than 74.5, which was 2 standard deviations or below 1 standard deviation below the mean. Okay, so that was one score. All right. And then in between 1 standard deviation below the mean and the mean, between 74.5 and 84.8, I had 6 scores. Okay? And then between 84.8 and 95.1, I had 7 scores. And then above 95.1, I had 2 scores. Okay? So that's what I had. So those are my 4 bins. And then I did O sub k minus E sub k squared divided by E sub k for each term, and I got a chi-squared value of 1.37 or so. Okay. Now you can look at this and you say, okay, well that's less than the number of bins that I've got, which is 4 bins, so that's a pretty good fit. But then if I want to calculate my reduced chi-squared, I could do that. So I look at it. Here's my chi-squared. My reduced chi-squared would be my chi-squared value, which is 1.37, and then divided by n minus c, where n is the number of bins, which is 4. And the number of constraints is 2, because you have to find the mean and the standard deviation, so that's 2 constraints, all right? And 4 minus 2 is 2. Take 1.37 divided by 2, and you get about 0.69, okay? So that's my reduced chi-squared value, okay, for this data set was about 0.69. And 0.69 is less than 1, so yet again, it's a decent fit, okay? So I'll make this file available to you online as well, so you can go through and figure out what's going on with all that. Okay, now, how do you evaluate whether something is a good fit or not? So there's a table in your book in Appendix D, okay, and that's the probabilities for chi-squared. And what this table does is give you the probability that you obtain a value of chi-squared that's larger than the one given in the table, okay? So if your chi-squared is near 0, for example, if you look over here in the table, let's see if I can get to a larger view. Let me zoom in here so that you can see a little bit better. Okay, so if I look here, here's my values of chi-squared. So if you look at your table, across the top of the table are chi-squared values, reduced chi-squared values. And then on the left-hand side of the table are your values of D, or the number of degrees of freedom. All right? So what you want to do is match up your chi-squared value, the closest to your chi-squared value, the number of degrees of freedom that you've got. All right, so for the example that we did, we had a chi-squared, a reduced chi-squared of about 0.7, and then we had D, number of degrees of freedom of 2. So if I go over here, here's 2, and then I go over to about 0.7? Well, I have in the table 0.6 and 0.8, all right? And then when I look in that table, I can see that for 0.6 it's 55, and for 0.8 it's 45, okay? So I'm going to call it about 50 because 0.7 is about halfway between that, and 50 is halfway between 55 and 45. So I got 50%, okay? So what this means is that you have a 50% chance, based upon what's going on with our data here, that you would have a chi-squared value larger than the one that you've got, okay? Now what does that mean? Well, if you've got, say, for example, a probability of less than 5%, all right, so these are out here in the less probable values. So in order to get to the less than 5% value here, I would have to have a chi-square value of a reduced chi-square value of 3. Okay, so that's a pretty big reduced chi-squared value, which would indicate not a very good fit, right? All right. So in particular, if your probability is less than 5%, then we say that this disagreement is significant, and you reject the assumed distribution at the 5% level. In other words, there's no way that this distribution is fit by a Gaussian distribution. It's not a good fit. Okay. If it's less than 1%, then the disagreement is highly significant, okay, and you can reject it at the 1% level. So we've got a 50% value, right, and 50%, that means the Gaussian is a pretty good fit. Okay, good chi-square values are roughly, reduced chi-square values are roughly 1. If you look at the values in this table for reduced chi-squared for various values of d that are roughly 1, then you can see it starts off at, say, 32%, and then it goes all the way down to, say, 47%. So if you're looking at 50-50 odds, then that's considered to be a good fit. There's a good likelihood that this function is well fit by the distribution that you've picked, if that makes sense. All right, you'll also notice if you go back and look at the table, which is online and in your textbook, that you can see that as you go to larger and larger values of the number of bins or the number of data pairs, which is your number of degrees of freedom here, D, if you go to larger and larger values, larger and larger sample sets, then you'll see that you get more confidence in the results with more data sets. So for example, your table kind of slants, okay, it kind of goes like this as you go across, and that means that for smaller values of reduced chi-squared, say here if you get a reduced chi-squared value of 1.8, all right, and you have 30 degrees of freedom, then that means that you can reject it, okay, whereas for the same value of reduced chi-squared, you can't reject it for lower data sets, or for smaller data sets, if that makes sense. Okay, so this sort of thing is the kind of thing that you really have to practice in order to truly get it. The aha moment will come in class when you do the worksheet, and I look forward to seeing you there.